Yep.
If you step outside on a clear, dark night, right, like far away from the glare of city streetlights,
Yeah.
you can usually spot the constellation Orion.
Oh, yeah, it's a classic.
Right. Most of us recognize the Hunter,
Yeah.
specifically those three bright stars in a neat diagonal row that make up his belt.
Exactly.
But if you drop your gaze just below that belt, you'll find his sword. And it looks like three fainter points of light hanging in a short vertical line.
Yeah.
But if you look closely at the middle one, like especially if you happen to have binoculars handy, you aren't looking at a crisp twinkling star at all.
No, not
You are looking at a smudge. And here's the secret about that smudge.
Yeah.
It's actually a live demolition site where hundreds of newborn stars are actively destroying the very cloud that created them.
It's wild, right? It just completely shatters the illusion that the night sky is this, static canvas of pinpoint lights.
Yeah.
Once you realize what you're actually looking at, that fuzzy little glowing patch becomes one of the most violent, dynamic places you can see with your own eyes.
It really is. And so our mission for today's deep dive is to take our stack of astronomical sources and use that exact smudge in Orion's sword to explore the entire incredible life cycle of stars.
It's a great journey to go on.
We are going to slow things down today. We want to break down these massive, mind-bending cosmic mechanics into everyday concepts. You absolutely do not need a degree in astrophysics for this.
Definitely not.
We're just going to look at the nuts and bolts of how the universe builds things.
Mm.
Okay, let's unpack this. What actually is that smudge?
Well, that smudge is the Orion Nebula.
Okay.
And it's located about 1,300 light years away from us. It is this vast, sprawling cloud of gas and dust, and deep inside that glowing fog, like at this exact second, hundreds of brand new stars are in the messy process of being born.
Wow.
Yeah, it is quite literally a working stellar nursery.
Okay, so before we could even get into the mechanics of how a star ignites, we have to understand the environment that makes it possible, right?
Right. The nursery itself.
Yeah, we need to move from just staring at a fuzzy patch in the sky to really understanding the physical reality of a nebula.
Sure. So nebula is simply the Latin word for cloud. Out in the interstellar medium, which is just the massive voids of space between existing stars, you have these sprawling clouds of dust and hydrogen gas.
Just floating there.
Right. But calling them clouds almost does them a disservice because of their scale. I mean, we are talking about structures that can span dozens, sometimes hundreds of light years across.
Wait, I need to stop you there because I want to make sure I'm wrapping my head around the physical density of this.
Okay, sure.
Because our sources say the material inside a nebula is unfathomably thin, like thinner than a laboratory vacuum on Earth.
Oh, absolutely.
So how does something that practically doesn't exist hold enough material to build a star?
It's a great question. The secret is sheer volume.
Well,
Yeah. The gas and dust are indeed spread out far, far more thinly than the air in the room you're sitting in right now. But because a single nebula covers trillions upon trillions of miles of space, when you sweep all that microscopic dust and sparse gas together into one pile,
you get a lot of stuff.
exactly, you suddenly have enough raw mass to construct thousands of stars.
That is just mind-blowing. But they don't all look the same, do they?
Yeah.
When we point a telescope at them, astronomers sort them into a few broad categories based entirely on what is happening to the light interacting with that gas.
Right.
And the Orion Nebula is the classic photogenic example of an emission nebula. It literally glows in the dark.
Yeah, and that glow is the defining feature of an emission nebula and has a very specific aggressive cause.
Aggressive.
Yeah, because buried deep within that particular cloud are extremely hot, massive newborn stars. They are blasting out intense ultraviolet radiation.
Yeah.
And this radiation is so energetic that when it slams into the surrounding hydrogen atoms, which, make up most of the cloud, it literally rips them apart.
It strips the electron right off the atom.
Exactly. That process is called ionization. It leaves behind a bare, positively charged proton.
But the universe doesn't like leaving things unbalanced.
No, it doesn't. So eventually, that wandering electron gets recaptured by a proton, and as the electron snaps back into its proper place in the atom, it releases a tiny packet of energy in the form of light.
And for hydrogen, that snapback process releases a very specific, distinctive shade of red light, which scientists call hydrogen alpha light.
Right. Now imagine countless trillions of hydrogen atoms doing this exact same violent dance.
Just ripping and snapping back.
Yes, ripping apart and snapping back together across a cloud that is light years wide. The cumulative effect is that the entire nebula lights up in a brilliant, soft red glow.
It's essentially how a neon sign works. You know, you have these young, ridiculously hot stars acting as the power source like the electrical current, and the massive gas cloud is just the glass tube lighting up around them.
That is a perfect physical equivalent. The star is the plug, the nebula is the bulb.
Okay, but what happens if the stars inside the cloud aren't those massive, hyper-hot monsters? Like, what if they're just average, run-of-the-mill stars that don't have enough ultraviolet punch to rip atoms apart? Does the cloud just stay dark?
Well, not necessarily dark, but it certainly doesn't glow on its own. And that brings us to the second category, which is the reflection nebula.
Okay.
In this scenario, the star isn't hot enough to trigger ionization. So the cloud is just sitting there, catching the starlight and scattering it in all directions.
But why do reflection nebulae almost always look blue in photographs? Like, if the star is putting out white light, why wouldn't the cloud just reflect white light?
It comes down to the size of the dust grains floating in the cloud. Fine particles scatter shorter wavelengths of light much more effectively than longer wavelengths.
Right.
Since blue light travels in shorter, tighter waves than red light, the blue light hits those dust grains and scatters wildly in every direction, bouncing into our telescopes.
And the red light.
The red light, with its longer, lazier waves, mostly just passes straight through the dust unimpeded.
Wait, isn't that the exact same physical reason the sky on Earth is blue during the day?
It is the exact same mechanism. It's known as rayless scattering.
Wow, okay.
Yeah. Whether it's nitrogen molecules in Earth's atmosphere or microscopic silicate dust grains in a distant nebula, they both catch and scatter blue light. So when you look at a reflection nebula, you are seeing a massive, faint blue veil draped around a star.
Think of driving through a heavy fog at night with your high beams on. The fog itself isn't generating any light, but all those tiny water droplets catch the beam of your headlights and scatter it, making the fog banks suddenly glow and become visible.
Yeah, the headlights in the fog is the perfect way to visualize a reflection nebula.
Okay, so emission nebulae glow red because atoms are being ripped apart, and reflection nebulae glow blue because dust is scattering starlight.
Correct.
But then we have the third kind, which kind of feels like a cosmic pothole, the dark nebula.
Oh, dark nebulae are fascinating. A dark nebula is entirely defined by what it hides. In some regions of space, the concentration of dust and gas gets so incredibly thick and dense that visible light simply cannot penetrate it.
So it's just a massive silhouette.
Exactly, a complete void. It looks like a black, jagged tear in the fabric of space, completely blotting out all the stars and glowing gas behind it.
The famous Horsehead Nebula is one of these, right?
Yeah.
Like if you look at a picture of it, it literally looks like a dark night piece from a chessboard rising up against the glowing red background.
It really does.
And if you live in the southern hemisphere, you can see one of these silhouettes without a telescope at all. It's called the coal sack, located right near the Southern Cross.
Yeah.
It just looks like someone took a cosmic hole punch to the Milky Way.
What's fascinating here is that all three of these types, the glowing red, the scattered blue, and the pitch black, they're all made of the exact same raw materials.
Just gas and dust.
Yes. The only difference is how that material is interacting or refusing to interact with the nearest starlight.
That's incredible. But, you know, just looking at the light show doesn't actually tell us how a star is born. To find the actual assembly line, we have to go deep into the coldest, darkest, most shielded parts of these clouds.
Yes, we do.
The regions astronomers call giant molecular clouds.
These are the vast freezing reservoirs where the actual construction of a star takes place. And when we say cold, we mean a temperature that is almost impossible to comprehend.
How cold?
Usually around 10 to 20 degrees above absolute zero.
Wow. Which is exactly why they are called molecular clouds, right?
Yeah.
Out in the open galaxy, it is far too chaotic for hydrogen atoms to bond. They just bounce off each other.
Right, there's too much energy.
But deep inside these dark nebulae, shielded from all that violent starlight by thick walls of dust, it is so quiet and so freezing cold that individual hydrogen atoms can finally slow down and pair up into molecules.
Exactly. It is the ultimate quiet room. And that frigid, undisturbed environment is the prerequisite for the longest, slowest battle in the universe to begin, the battle that actually makes a star.
It's a huge jump from a freezing cold, quiet cloud to a blazing million-degree sun. What actually pulls the trigger?
Well, the architect of every star is gravity. But gravity doesn't get to just win immediately. It's a delicate, agonizingly slow balancing act.
Okay.
Every single speck of dust and molecule of gas in that enormous cloud is exerting a microscopic gravitational pull on every other speck around it. Gravity is relentlessly trying to draw all this material inward, trying to crush it into a single point.
But the cloud pushes back.
Yeah, it pushes back with pressure. The gas has an inherent outward pressure, and the cloud itself is swirling with chaotic, turbulent currents. So for millions of years, you have a stalemate.
Just stuck there.
Yep. Gravity pulling in, pressure and turbulence pushing out, the cloud just hangs there, suspended in tension.
Here where it gets really interesting. That stalemate can't last forever because space isn't an empty void. Things bump into each other. All it takes is a single trigger from the outside to tip the scales.
That's right. Often, that trigger is the shock wave from a dying star, like a supernova exploding nearby and slamming a wave of force into the molecular cloud.
Or maybe the cloud slowly drifts into a galactic traffic jam, like a denser spiral arm of the Milky Way.
Exactly. Whatever the external push is, it compresses a pocket of that gas just enough that gravity finally, decisively, gets the upper hand.
And once gravity outweighs the outward pressure, that specific pocket of gas begins to collapse inward. And it becomes a runaway train, right?
Oh, totally.
As the material falls toward the center, it gets closer together, which makes the gravitational pull even stronger, which yanks more material in even faster.
And as it collapses, the physics of thermodynamics take over. The center of that collapsing clump begins to heat up dramatically.
Think of a standard bicycle pump.
Oh, that's a good analogy.
Yeah, if you've ever pumped up a flat tire vigorously, you know the metal valve at the bottom gets surprisingly hot to the touch?
Yeah.
When you forcefully squeeze a gas into a smaller and smaller volume, its temperature inherently skyrockets. So now you have this gargantuan clump of space cloud getting mercilessly squeezed by its own gravity, and the core is getting hotter and hotter.
And that increasingly dense, sweltering core at the absolute center is what we call a protostar. It is gathering the mass it needs, but it hasn't earned the title of star quite yet.
It is a star in waiting.
Exactly. For hundreds of thousands of years, a continuous rain of gas and dust falls from the surrounding cloud down onto the surface of this protostar. The core gets heavier, tighter, and hotter.
Until it hits a very specific magical threshold.
Tens of millions of degrees.
Wow.
Yeah. If the protostar gathers enough mass, the crushing pressure and the unimaginable heat at its absolute dead center force, a change in the fundamental nature of the atoms, it triggers nuclear fusion.
Which is the defining mechanism of a star. Hydrogen nuclei naturally want to repel each other, right? Like two magnets facing the same way.
Right.
But gravity and heat force them together so violently that they literally fuse to form helium.
And that fusion process unleashes a self-sustaining thermonuclear flood of energy. The very second that nuclear fusion ignites and pushes outward, counteracting the crushing weight of gravity, a star is officially born. It achieves a new balance.
But they don't just pop out of the cloud one at a time, do they?
Yeah.
I mean, a giant molecular cloud holds enough material to build thousands of stars.
Oh, no. They are overwhelmingly born in groups.
Okay.
The parent cloud fragments into dozens, hundreds, or even thousands of collapsing clumps, all at roughly the same time. The result is what astronomers call a star cluster.
I love the idea of a billion toddler stars bumping into each other. The sources actually highlight two completely different types of these stellar families. Let's look at the first one, the open cluster. This is exactly what is currently forming inside the Orion Nebula, isn't it?
It is. An open cluster is a relatively loose gathering of anywhere from a few dozen to a few thousand stars.
Okay.
And because they all condensed out of the same parent cloud, they share the exact same chemical makeup and are all precisely the same age.
The Pleiades is a brilliant example of this. You can easily spot it with the naked eye. It looks like a tiny, glittering little dipper of stars clustered closely together.
Oh, yeah, the Seven Sisters.
Right. It's an open cluster, and at only about 100 million years old, it's basically a group of cosmic newborns. But here is the tragic twist. Open clusters are doomed.
Yeah, they really are. They cannot hold themselves together. Their mutual gravity just isn't strong enough.
So what happens?
Well, as this loose family of stars orbits through the dense, gravitationally chaotic disk of the Milky Way, they're constantly being tugged at.
It's death by 1,000 cuts. A passing giant molecular cloud tugs one star away. The subtle background gravity of the wider galaxy pulls at the edges. Even the sibling stars themselves gravitationally nudge each other out of the nest.
Exactly. Over the course of a few 100 million years, the cluster simply dissolves. The individual stars drift away, evaporating into the vastness of the galaxy. They survive, but the family unit is permanently disbanded.
And this isn't just an abstract astronomical concept. This is the story of our own solar system.
It is.
Our sun is 4.5 billion years old. It almost certainly formed in a bustling open cluster, just like the Pleiades. but its sibling stars drifted away billions of years ago. Today, we have absolutely no idea which of the hundreds of billions of stars in the Milky Way are our sun's actual littermates.
They are just lost in the crowd.
Yeah, it puts our isolation in perspective, but it also provides a stark contrast to the second kind of stellar family, the globular cluster. Because if open clusters are temporary, drifting camps, globular clusters are ancient, impenetrable fortresses.
Yes. The sheer scale of them is hard to wrap your head around. A globular cluster is a tightly packed, perfectly spherical swarm of stars.
We're not talking a few thousand anymore, right?
No, we are talking about hundreds of thousands, sometimes millions of stars, all violently crammed into a region of space only tens of light years across.
Wow.
The core of a globular cluster is so dense with stars that the night sky on a planet inside one would be permanently blazing with light.
But why don't they get pulled apart like the open clusters do?
It comes down to mass and location. Because you have millions of stars bundled together, their combined gravitational anchor is virtually unbreakable. The wider galaxy just can't tear them apart.
Makes sense.
Furthermore, they don't orbit in the crowded galactic disk where collisions happen. They orbit way out in the sparse, empty halo surrounding the Milky Way.
And they have been out there for a very, very long time.
If we connect this to the bigger picture, globular clusters are relics. They formed during the chaotic, turbulent youth of the universe well over 10 billion years ago.
Wow, 10 billion.
Yeah. So when you look at a globular cluster like Omega Centauri, you are peering at a living fossil from the dawn of the galaxy.
So we have ancient stars safely locked in fortresses and young stars drifting apart. But I want to pivot back to that moment of birth for a second, because the act of a new star turning on is devastating for the nebula around it, isn't it?
Oh, absolutely. The creation of a star is fundamentally a destructive process.
I was
Well, the moment those massive new stars ignite, that same intense ultraviolet radiation that causes the nebula to glow red begins to systematically tear the cloud to shreds.
It's a dynamic demolition process called photoevaporation.
Right.
These blistering young stars are throwing off hurricane force, stellar winds, and radiation, physically blowing the remaining dust and gas outward, carving out massive, hollow cavities in the stellar nursery.
The star consumes what it needs and violently ejects the rest.
Which totally recontextualizes one of the most famous space photographs ever taken. The pillars of creation in the Eagle Nebula.
Oh, yes.
We've all seen the posters, these towering, majestic, solid-looking columns of cosmic dust. I always assumed they were permanent monuments in space. You're telling me they are actually melting away.
They are actively being destroyed. The pillars aren't monuments. They are just stubborn fingers of dense gas that are temporarily resisting the brutal radiation winds blowing from nearby massive stars.
They're being sandblasted away.
Exactly. Give it a few million years, and the photoevaporation will likely erode those pillars completely, exposing the newer protostars still hiding inside their tips.
So the larger environment gets blasted away. But if we zoom all the way in, right down to the immediate neighborhood of a single baby star, the leftover dust is doing something incredible.
Yes, it is. As that original clump of gas collapsed inward to form the star, it carried a tiny amount of rotation. And as it shrank, it spun faster and faster.
Think of a ball of pizza dough. When a chef tosses a round ball of dough into the air and spins it, the centrifugal force naturally flattens out into a wide, flat disk.
The physics in space are identical. The collapsing cloud flattens into a wide, violently spinning disk of gas and dust surrounding the central protostar.
We call this a protoplanetary disk.
Right. And while the star is monopolizing the center, the leftover debris in the disk is quietly getting to work.
Through gentle, incredibly slow collisions, dust grains stick together, they become pebbles. Pebbles crash together to form boulders. Boulders gravitationally attract each other to form asteroids. And over millions of years, that chaotic bumper car arena builds planets, moons, and comets.
A nebula isn't just a stellar factory, it is a planetary assembly line.
I love that.
The exact same collapsing cloud that built the sun simultaneously provides all the raw building blocks for an entire solar system.
Let's bring that right down to the listener. The iron in your blood, the calcium in your bones, the actual rock under your feet. Every single atom of it was baked in one of those spinning protoplanetary disks billions of years ago.
You are sitting on the recycled debris of a stellar nursery.
Okay, I have to call a timeout here. We've painted this incredibly vivid picture of glowing red clouds, blue veils of dust, melting pillars, and spinning disks.
We have.
But when I look at those jaw-dropping, insanely detailed photos from the Hubble or James Webb telescopes, I have to ask, on behalf of the skeptical listener, are those colors actually real? Or is NASA just basically photoshopping the universe to make it look cool for a magazine cover?
This raises an important question, and it is the most common question people ask when looking at astrophotography. It deserves a nuanced answer.
Okay.
Sometimes the colors are quite literal. The deep reds of the hydrogen emission nebulae and the blues of the reflection nebulae are visually accurate.
Oh, really?
Yeah. If human eyes were millions of times more sensitive to light, that is roughly what you would see floating in space.
But the hyper-detailed ones, like the pillars of creation with those vibrant golds and deep cyan blues, those use something called the Hubble palette, right?
Yes, the Hubble palette is where the art meets the science. When scientists look at a complex nebula, they are trying to understand its chemical structure.
Right.
So they use filters that only capture very specific, narrow wavelengths of light emitted by specific ionized elements, usually sulfur, hydrogen, and oxygen.
But if you just looked at those three elements naturally, they mostly emit light in the red part of the spectrum.
Yeah.
The whole picture would just look like a blurry, monochromatic red smudge.
Exactly the problem. Human eyes are terrible at distinguishing subtle variations of red.
Right.
So to understand the structure, scientists meticulously assign those invisible or overlapping chemical signatures to distinct color channels. They map sulfur to red, hydrogen to green, and oxygen to blue.
By doing that, you aren't faking the image. You are taking invisible chemical data and mathematically translating it into a visual format that our brains can actually read.
Exactly.
It reveals the intricate three-dimensional structure of the gas that would otherwise be entirely invisible to us.
It is a scientific translation, not a deception. It allows us to comprehend the sheer complexity of the universe's architecture.
I love that. Translating the invisible so we can witness the mechanics of creation. Which brings us right back to where we started. You, standing under a clear, dark sky, looking up at the constellation Orion.
Full circle.
The next time you spot that faint fuzzy smudge in his sword or catch the glittering little cluster of the Pleiades out of the corner of your eye, remember that you aren't just looking at pretty ceiling decorations. You are looking at a live demolition site. You're watching gravity patiently, relentlessly defeating pressure.
You are witnessing the exact same physical processes that built the star you orbit every single day.
So what does this all mean? It means we are connected to that smudge in a very literal way. The chaotic, drifting litters of stars born from those clouds are the reason we're here.
Which leaves us with a truly provocative thought to mull over tonight. We know our sun formed in one of these crowded clusters.
Right.
It formed a planetary system with the exact right conditions to support life. Its sibling stars, born from the exact same parent molecular cloud, carry the exact same chemical ingredients and the exact same building blocks.
And they're still out there.
They are out there right now, scattered anonymously across the Milky Way. Could one of those long-lost sibling stars be quietly warming a planet with life of its own tonight?
A lost twin to our solar system, completely unaware of us. Something to think about the next time you look up. Thank you so much for joining us on this deep dive. We'll catch you next time.